Okay. 5, 6, 10, 11. All right, so this is going to be probably pretty brief because we've already talked about pretty much everything that's in 5, 6, 5, 10, and 5, 11. It's about collision energy. And we talked about how in order to make a successful reaction, you have to have the proper orientation. You have to have the proper amount of energy to get them to stick. And then the concentration and the particle size and the pressure is the frequency at which they stick. Okay? So pretty much everything that is relevant to this we've already done. Well, let's go ahead and make sure we've checked all the boxes. Up. Hey, up. There we go. There we are. Okay. So, again, this is just a lot of minutia. It's a lot of minutia of the concepts that we've already talked about. Okay, concentration means greater frequency of collisions. Catalyst presence will improve orientation, and then temperature both adds the amount of energy you need for a favorable collision and the frequency of collisions because you have the particles moving faster. Okay. So that's the real thing you got to remember is when it's talking about increasing particle frequency or particle collision frequency, it's temperature and concentration. And concentrations analogs are particle size for a solid and pressure for a gas. Okay. Increasing pressure is like increasing concentration. And increasing particle size increasing particle surface area is like increasing concentration. So when you crush a powder, or when you crush a solid into a powder, you've increased the surface area for a solid. Okay. Is that clear? All right. So not every particle triggers a concentration of gas. So we talked about this. A plus B is our reactants. A plus BC is our products. And our transition state is ABC. And this is obviously an exothermic or endothermic reaction. It's exothermic. And when you do the AP, when you see a graph like this, the graphs that you see will be exaggerated. Like the products will be very different than the reactants. And when you draw diagrams, you should also make it exaggerated. Show that it is a clear difference between products and reactants. So the change in energy, once again, this is just like last year, we talked about enthalpy. The change in energy in the reactions of products is the overall reaction energy. And then the energy that you need to get up to the transition state is called the activation energy, the energy of activation. So this is basically how much energy the particles need to get a favorable collision. If you don't have enough energy to get a favorable collision, then you're just not going to have a reaction. You have to have enough energy to get over the hump and get a favorable collision. Okay. So far, so good? Any questions so far? I'm just going to talk until we encounter something new. One that I do want to talk about is the reverse reaction. Will the reverse reaction have the same magnitude of delta E? So if you're going backwards, so if you flip it over and you're going from products, in this case, the products to the reactants, will the delta E be, the magnitude be the same? Yes. The sign will be different, but the magnitude will be the same. For instance, if we went from 100 to 80, then we would have 80 minus 100, negative 20. And if we went to 80 to 100, 100 is minus 80, we have a positive 20 delta E. So the magnitude of the energy of reaction will be the same, the sign will be reversed. What will not be the same is the energy of activation. So take a look. When you go from reactants to the intermediate state, you have a smaller energy of activation than if you go from products to the intermediate state. Okay. So that sometimes gets tested. A reverse reaction is going to have the same magnitude delta E with the sign reversed, but the magnitude of the energy required to overcome the hump is going to be dependent if it's a exothermic or an endothermic reaction. Capiche? All right. Okay, yeah, all right. And we talked about collision energy. Once again, when you're drawing an energy distribution, you should start at 0, at the basically activation energy, and you need to come down, basically, ideally, start at 0, end at 0. The wider the hump represents a higher energy. And the spike at the top, that represents the average kinetic energy or the average temperature. Great. That. Unimolecular, don't have to worry about that. We talked about that. We talked about that. We talked about this. Exothermic, endothermic, we talked about. Forward reaction, reverse reaction, we just talked about. We're comfortable with this forward reverse stuff? Okay. Multi-step, we've done this a million times. So the actual mechanism matches the stoichiometry. The rate law does not match the stoichiometry, but the mechanism does. And the rate law matches whatever the slow step is. And again, this is the proper way this is the way the AP is going to do it. Each step is a hump. 1 step, 2 steps. It's just the way they're going to do it. Is the Arrhenius equation on your formula chart? Kinetics, it is not on your formula chart. I don't see it anywhere on your formula chart. So you don't have to worry about it anymore. Yeah, the Arrhenius equation used to be on your formula chart, and basically all it is a way of referencing the speed of a reaction to the energy or to the reaction conditions. And it should make a little bit of sense that if E is very small, you're raising a small negative E. If EA is very small, the hump is very small, you're going to have a very large K. And if E is very large, you have a gigantic hump, you're going to have a very small K. Okay? This equation, again, if it's not on your formula chart, you don't need to know it, but you do need to understand what it's telling you. And that is that a larger activation energy on any hump will correspond to a smaller rate constant. In other words, the rate constant is kind of like the judge of how fast the reaction goes. It is ultimately what controls the reaction regardless of the concentration, pressure, or whatever. Okay. A is a constant, R is just a gas constant, T is a temperature. And it also should make sense that if you increase the temperature, what happens to K? Increase T here, what happens to K? A lot of sign flipping going on here. You are raising something to a negative exponent. So that means if your exponent is larger, your number is smaller. If your exponent is smaller, your number is going to be larger. Because negative doesn't make it a negative exponent doesn't make it numerically negative. It makes it larger or smaller than 1. So a negative positive thing means your E is going to be smaller than 1. A negative than a really big thing, a negative large value means you're going to be much, much smaller than 1. And negative positive value is going to be much, much larger than 1. So if your temperature, which is in the denominator, becomes larger, your K value becomes larger. Because this is negative small, raised to a negative small. If your temperature becomes smaller, this number here gets larger, and your K value is going to get smaller. It's not going to become negative, it's just a magnitude thing. Okay, how are we doing? Do we understand this? I mean, it makes sense conceptually that higher temperature, larger K, faster reaction. Lower temperature, smaller K, slower reaction. And although you're probably, I don't think you're ever going to have to do math with that Arrhenius equation, just to realize that if you ever had this kind of situation, you have to have T in Kelvin. Okay. If you're comfortable with this concept, give me a thumbs up. Again, it's not on the formula chart, means you don't have to use it, but you do need to understand it, understand what the concept behind it. Okay, then there's all the math that you already learned the equations, the change in concentration minus over time equals negative KT, natural log of change in concentration equals negative KT, and 1 over concentration equals KT, those 3 equations. Okay. And the bulk of what you need to be able to do with those equations is, if needed, do it in an FRQ, do the math in the FRQ. But more importantly, know that the reaction graph corresponds to which of those two. Again, straight line for concentration versus time, 0th order. Straight line for natural log over time, 1st order. Straight line for inverse over time, or concentration over time, 2nd order. And the K value is the slope for 2nd order, the negative slope for 1st order, and the negative slope for 0th order. With this? Yeah, that's basically all of this. Yeah, don't have to worry about that. This is per time. Okay, yeah, whatever. Again, I don't think you have to use the Arrhenius equation at all in the AP anymore. All right, let's bang these guys out. Table below outlines the results from 3 experiments which were conducted at the same temperature involving the same, again, the same temperature is important, otherwise you can't compare them. So the results show the initial rate increased when the initial concentration of either reactant increased, which should. Explain why increasing the concentration or partial pressures of a reactant can increase the rate at which the reaction proceeds. Think about this for a second. I'm going to ask for a volunteer. How would you answer A? We all know the prompt is true. It's giving us the prompt, but how would you explain it in terms of particle model? I can get big. Okay, who wants to volunteer their answer? Who wants to throw themselves on the altar of learning? Shane, what do you got?
Increasing the concentration or partial pressure will increase the rate because it will lead to more likelihood of the particles interacting with the proper faces to create a bond.
I'm glad you said that. That's wrong, because you need to talk about collision frequency. That's what we need to use. When you're talking about concentration or pressure, it's all about more particles per unit area or unit volume increases collision frequency. It doesn't increase. It doesn't change the orientation. It just means more collisions are likely to create additional favorable reactions.
Could you talk about how the rate is molarity over speed, and then talk about the collision reaction?
I wouldn't even talk about any kind of formulas.
Okay.
I would just look at that and say, they want you to know, or they want to know from you, do you understand that concentration means more particles per unit volume? We don't know about temperature. It hasn't changed about temperature, so we don't know their speed. All we know is there are more particles per unit volume. That's going to increase collision frequency. We don't know anything about energy. We don't know anything about orientation, just collision frequency. Is that clear? Part B. What environmental factor could be altered in order to increase the initial reaction rate in experiment 1 if the initial concentrations of the reactants remain the same? And we come down here. Oh, can I scroll? I will just scroll. Let me scroll. There we go. Okay. There are 2 environmental factors that we could alter that would increase the initial reaction rate in experiment 1. What are those 2 and why?
Temperature.
That's the big one. So temperature is a big one. If you increase the temperature, you increase the energy of the reactants and how fast they're moving. So what environmental factor can be altered in order to increase the initial reaction rate in experiment 1 if the initial concentration of the reactants remain the same? Temperature. Okay. So that's the big one. That's the one I would lean on. When you increase the temperature of a reactant, that increases the energy of each particle. You can say average kinetic energy of each particle, which is even better, which increases the collision frequency. We don't know anything about the favorable collision orientation, but we do know the other one. Now, and again, I said there's 2, but the other one's kind of ticky-tack in that it talks about concentration. You could technically increase the pressure of the reaction vessel as well. That would increase the collision frequency, but I think I'd fall back on temperature. All right, is that clear? What we just talked about for part B? Part C. What is the order of reaction with respect to N2? Show your work. So you can do this. What reactions should we use to determine the order of NO?
1 and 2.
1 and 2. So oxygen's held constant. Going from 2 to 1, we doubled the concentration. And what happened to the rate? Quadrupled. Yeah. So quadrupled. So we would consider the order with respect to NO to be what order? Second order. Exactly. And then order with respect to oxygen. Which reactions do you want to use for oxygen?
2 and 3.
2 and 3. Going from NO is held constant. Going from 2 to 3, you doubled the concentration, and the rate doubles. So we would say this reaction is first order with respect to oxygen, second order with respect to NO, and how would you write the rate law? Whenever it says rate law, write the whole thing.
Rate equals K, NO2, and then oxygen.
NO second order,
Second.
oxygen first order. Good. That's what you're. You would not believe how frustrating it is as an educator when we see just that part. This earns no points. You got to show the whole thing. It happens every year. Darn it! Why'd you? Oh, you missed the point. Okay. Overall order of this reaction is third order. And find the rate constant for the reaction. Okay. So now we need to find the rate. Actually, find the rate constant and the units. So the default is always to use the first reaction. So go ahead and bang that through. We need to get the units and the numerical value of the rate. Again, first reaction is, first experiment is always the default we use. It shouldn't be that different from any others, but let's just always use the first one. Unless it says specifically from any other reaction. Does your work kind of look like my work?
1721, I believe.
Am I good? 17.2. Okay, so I'll take it. 17.2. And then our units. Again, this is going to be squared molarity.
Oh, 1721 as in 1700.
I won't round sig figs right now. 1721. Okay. And this is molarity squared. This is molarity. So what does our unit of K have to be?
1 over molarity squared second.
Yes, 1 over molarity squared seconds. Also, you could write it as molarity -2, second -1. Either is okay, depending on your preference of, I like to show exponents this way. All right, cool. If the same 3 experiments were conducted at a lower temperature, would the magnitude of the rate constant be greater, less, or equal to the value calculated above? Justify your answer. And 10 years ago, you could say, well, the Henderson or the Arrhenius equation says this. They don't want you to care. They don't care about that anymore. But how would you respond? If these experiments were conducted at a lower temperature, would the rate constant K be higher, lower, or the same? And justify your answer.
Lower.
Why? It is a little lower. Why?
Because temperature decreases the amount of collisions.
How?
Because
Favorable collisions.
favorable collisions. Because kinetic energy is less. Average kinetic energy is lesser.
Of the
Of
particles.
the particles is lesser.
So they would collide
Less.
less frequently. And because they're carrying less energy, the number of collisions would create fewer favorable collisions. Okay. So again, temperature slows the particles down and reduces their overall energy they're carrying. So the number of favorable collisions is going to be reduced due to slower particles, lower collision frequency, and particles carrying less energy, less likely to overcome the energy barrier with each collision. Gotta be specific. I know it sucks, but you gotta check all the boxes. That's how you turn a 4 into a 5, is you give the grader exactly what he's looking for, or she's looking for. All right, how are we doing with number 1? We comfortable with this? All right. Not all collisions between reactants result in formation of different products. Explain what this is. So it doesn't say how many, but just not all collisions between reactants result in the formation of products. Explain why this is. What factors would be working against you to get a favorable collision? Orientation, good.
Energy.
And energy, yeah. Orientation of the particles striking each other and striking with enough energy. I like to use a Lego analogy. You could just go, tap, they don't stick. Or you could go stud, stud, and you're like, they don't stick. So they have to have enough energy and they have to have a favorable collision. Good. What is the difference between EA and delta E? Go ahead, Hank.
Delta E is 100 to 80, so it's the amount of energy that's lost in endothermic or exothermic reactions. And then EA is it's due to the rate. Isn't the gain from exothermic to endothermic?
EA is the energy of activation that each collision must overcome. So EA is the energy of activation that each collision must overcome. And delta E is the energy of reaction. Positive for an endothermic, negative for an exothermic, EA always positive because you have to overcome that energy lump. I would be surprised if they didn't even give you good. I would be surprised if they wouldn't give you points for it's the hump the reaction has to overcome, or the collision has to overcome. But it is the energy of activation that each collision must overcome to be a favorable collision. And delta E is the total energy of reaction. Positives for endothermic, negative for exothermic. Any questions on number 3? Banging right along. Okay. This is a great one. Energy profile diagram was plotted for the following second order reaction. You got it all in there. Second order reaction. At low temperatures, a relatively small fraction of collisions between reactants result in the formation of products. Makes sense. Describe the interactions between reactants that collided with an orientation that would produce products, but failed to do so. So they're saying not a lot happened. They had the proper orientation, but they didn't have a favorable collision. Why?
They didn't have enough energy.
Exactly right. Yeah. They did not have enough energy to overcome the energy barrier. They were not carrying enough activation energy to overcome the energy barrier. Clear? Okay. So there's EA. Whoop, there's EA right there from here to here. If a collision doesn't carry enough, it goes whoop, and then right back there. At high temperatures, a relatively large fraction of collisions between reactants result in the formation of products. Describe the interaction between the reactants from the moment of a collision through the formation of separate products. I'm gonna say they're probably not gonna ask you for this, but give it a shot. How would you respond to this? Probably a little more specific than they're going to test, but just in case. There's always going to be something that's going to separate the 4s from the 5s. Anyone want to give it a shot? Everybody's participating, which is great. No? Okay. The reactants collide to produce the activated complex up here. The reactants collide favorably with enough energy in the proper orientation to create the activated complex. The activated complex then becomes the products. That's how it works. You gotta form the activated complex. Okay. Again, I don't know that you're ever going to see this tested, but just in case. Draw a two-step reaction profile that satisfies the following conditions. Okay, so this is just like a little diagram, the little worksheet we had. We had to draw the humps. So show the activation for energy for each step and the overall energy change. We don't have any numbers, that's okay. The first step is the rate determining step. The first step is endothermic. The second step is exothermic. The overall process is exothermic. Give it a try. So you can do progress. You can do reaction coordinate. It's called the reaction coordinate. But I just like to call it progress. You could even do time. No one's going to care. This is energy. They do care about this one, though. What's that graph going to look like? If you makes a glove, that's just like sandpaper on the side. I need to smooth out my atoms. Okay. That's going to be hard with a sphere, which is like duct tape a piece of sandpaper to my hand. Let me know when you're ready. Good. Okay. Did you make a really big hump to begin with? Is your first hump bigger than your second hump? That's the most important thing. Because if the first step is the rate determining step, the first hump needs to have the largest EA. The rate determining step is going to be the one with the largest EA. And it says the first one is endothermic, so let's go stop right there. Ooh, that's bad. So I'm going backwards. There we go. Second step is exothermic. So we can go. That makes it exothermic. And it says the overall process is exothermic. So this guy's got to come down and drop below the original value. How about that? There's EA2. There's EA1. And this is delta E. You get the idea, but I want to be correct here. Okay, so first one's endothermic, stops at a higher energy value. Second step's exothermic, and the overall reaction is exothermic. And the EA for the first step is larger because it is the rate determining step. How do you feel about this? Any questions? All right, cool. Chemical reaction takes place in a beaker you're holding. While the reaction is taking place, your hand feels cold. Sketch a reaction energy diagram for the reaction. Is the reaction exothermic or endothermic? They're answering exactly the same questions. If you're holding a beaker and your hand feels cold, is energy going into the system or out of the system? It's going into the system. So it's just an endothermic or exothermic process. Endo. Okay. You are the surroundings, and energy is going from you into the system. Hence, it's getting colder. So this is an endothermic process. Should the right side be higher or lower than the reactants? Higher. Make a hump, have it end higher. This is a great question. This shows up on pretty much every multiple choice test in some form. The graph below can be used to find the activation energy EA for the chemical reaction. Label the y-axis on the graph.
Energy? Oh, wait.
X is 1 over T, so K to the negative.
Yeah. This is per temperature. Oh, you know what? Sorry. This is not tested. This is not. If this was time, it's not temperature. This was time, you could look at it and forget about it. This is not going to be tested. Never mind. Forget about that. Sorry. Because
Wait there for a
again,
second.
okay. So the reason this is here is because you could use the Arrhenius equation EA to make the slope the minus RT over EA. Minus EA over negative RT. But you don't do this anymore. We don't use the Arrhenius equation anymore. So you don't have to worry about that. I thought it was something else. I thought it was this equation. Where they have a graph, and this is time, and this is a box, and then they give you a line like this or a line like this, and they give you some information about the reaction. Remember, half-life is always first order. That's the big one. Always. All right. Let's bang out the last unit, which is catalysts. And again, this is going to go crazy fast because you already know what a catalyst does. What does a catalyst do? How does it do it?
Decreases EA.
Decreases the energy. Basically, it gives you another path that decreases the activation energy. And more specifically, how does it decrease the activation energy?
It increases the odds of a favorable collision.
By doing what? It's totally true.
Doesn't it put things in the right orientation?
Exactly. It increases the rate of it decreases the energy of activation, increases the rate, increases the odds of a favorable reaction by orientating is not a word, by orienting the particles more favorably. That's what a catalyst does. It creates a system where they are oriented in a more favorable direction, more favorable condition, lowers the activation energy, increases the frequency of a good reaction, and so on and so forth. And to know you're seeing a catalyst, it should be a reactant and a product. And it definitely should be exactly the same ratio. If there's 2 in the front, there got to be 2 in the back. So no catalyst. It doesn't change the type of reaction. So here, this is exothermic. Here, this is exothermic. It doesn't change that. It just changes the EA. Squish. And anything else we need to talk about? Okay, so there's a thing called homogeneous and heterogeneous catalysts. This is all irrelevant anymore. They don't care about that. The only thing you might see is something called a heterogeneous and homogeneous catalyst. A homogeneous catalyst is the same phase as your reactants. A heterogeneous catalyst is different phases than your reactants. For instance, your catalytic converter under your cars, but not mine, is a heterogeneous catalyst. It's a solid catalyst that reacts in the gas phase. So it's a surface catalyst. Yeah, that's how it works. All right, cool. That's all done. I don't even know if is there any exercises? Ooh, there is. Okay, cool. Whee! All right, this is what I was talking about. This thing right there. Okay. So time, natural log. That's. What is the difference between a reaction intermediate and a catalyst? Yeah.
A catalyst is at the start and the end of the equation.
And an intermediate is?
It gets canceled out through the steps.
It gets created, then consumed.
Created then consumed.
An intermediate is created in one step and consumed in a future step. Yeah.
Could just say the intermediate doesn't affect the EA, but the catalyst does.
I wouldn't. Okay. Yeah. Because if an intermediate was not there, that's a totally different reaction pathway. So I would, yeah, I wouldn't go that far. So yeah, a catalyst does reduce the activation energy, but I would say, like Ben was alluding to, a catalyst is a reactant and a product. It is not consumed. An intermediate is created and consumed. Okay, so there's an intermediate paragraph. Draw an approximation for the plot for the process of a catalyst. So what they're going to look for if you get this is, does it start and end at the same place? But is your EA smaller? So they're gonna, it's basically you're gonna be a 2-point exercise, and it's gonna be, does it start at the same place? Does it end at the same place? But is the hump smaller? Label the activation energy and the change in energy for the catalyzed reaction. There is your EA. There is your delta E. And this gets back to Hazel's point, explain why the presence of a catalyst increases reaction rate. It creates a more favorable orientation for the reactants. Doesn't do anything to the concentration, doesn't do anything to the temperature, it just creates a more favorable orientation. Is that process exothermic or endothermic? Endo, how do you know?
The products are higher than the reactants.
Yeah, products are higher energy saving reactants. All right, cool. Comfortable with number 2? We're almost done. This is a long lecture. I thought it was going to go faster. Anyway. The graph below shows the plot of natural log of A versus time for the first order uncatalyzed process. Oh yeah, this is great. The rate law for the overall reaction is rate equals Ka. It's first order. Draw a line that approximates the plot of the process in the presence of a catalyst. What would you do? Would you make it a larger slope? A smaller slope? Would you start at a different place? Would you end at a different place? Well, how would you draw that? Go ahead and give it a shot. Remember, K is the negative slope for first law, for first order rate law. It's a negative slope and straight line for natural log for first order. All right. I'll give you 30 seconds. All right, what would you do? I'm sorry? Keep going, yeah. Start at the same place and go, wee. So this M equals the negative slope, K equals the negative slope, and here K prime equals the negative slope. So more steeper, faster, reaction's faster. And I start at the same place because the reaction is not going to change the concentration. Huh? Good. Last 2 questions, then we're done. What is the difference between a homogeneous catalyst and a heterogeneous catalyst? In your own words, what did I just say 5 minutes ago?
Same or different phase as the reactants.
Exactly. Homogeneous literally means same stuff. Homogeneous catalyst is the same phase as your reactants. Heterogeneous catalyst literally means different stuff. It's a different phase. The catalytic converter in your car, heterogeneous. The enzymes in your blood, homogeneous. Okay? As the catalyzed reaction proceeds, does the net concentration of the catalyst increase, decrease, or remain the same?
It would remain the same.
So what? Exactly. If it's a catalyst, it is used in the reaction, but then remade. And every time the reaction proceeds, the same number of moles of the catalyst get used up and remade. So it does not change. If it does change, it's a reactant or a product, not a catalyst. And I think that is it. All right. How are you feeling about this stuff? Cool, because we're just about done. What do we have left to do? I think it's just the progress check on the unit test. So, yeah. So we have APCs tomorrow. 511. Oh, just one. Wow, this is a pretty weak day. That's okay. So we have ABC 511 MC and FRQ. Then you do the progress check. We go over the progress check on Wednesday. Our unit test is Thursday. We go over the test on Friday. Eh? Aren't you glad you do a test on Friday?
Yes.
And dream. And